Welcome back. Today we're going to talk about confidence intervals and a little about the paradigm shift associated with moving from point estimates and descriptive statistics to interval estimates and inferential statistics. If you're not comfortable with probability distributions, that is, the area under the curve between two z-scores, and you aren't at least beginning to get comfortable with the idea of standard errors, or the standard deviation of the estimate, I recommend you reread these sections or rewatch the videos associated with them before jumping in here. That said, to many people, confidence intervals make more intuitive sense than the central limit theorem and the other statistical details that underlie them. Confidence intervals are in fact only a small step past the central limit theorem of the CLT. As you may recall, the CLT lets us calculate the standard error, which is analogous to a standard deviation of samples in a sampling distribution. What's more, we can use the information on the spread of values in our sample to estimate a standard error even if we don't have more than one sample, which is usually the case. As a reminder, the formula for that standard error of the mean, there are other kinds of standard errors too, is the standard deviation divided by the square root of the sample size, or sigma divided by root n. There are a few things that work together to make this next bit of magic happen. First, the mean of a random sample is an unbiased estimator of the population mean. That is, it's not necessarily totally accurate, but it's equally likely to be high or low. Second, the standard deviation of the sampling mean, or the standard error of the mean, can be calculated from one sample. And finally, we can estimate the probability if a value falls within a given number of standard deviations of a mean. So, if we have an estimate of the mean and a standard error of the estimate, we can replicate what we did for a single case, that is, estimate the range that 99 or 95% of possible values might fall between, using our sample mean as the case level. When this range is estimated for a statistic instead of a raw score, it's called a confidence interval. And now, you have all the tools you should need to estimate a confidence interval. Let's work through an example. Assume we take a simple random sample of 100 people and find that the mean U.S. household income in that sample is $50,000 with a standard deviation of $20,000. The standard error of the mean, as I said, is equal to the standard deviation, 20,000, divided by the square root of the sample size. The square root of 100 is 10. So in our example, the standard error is 20,000 over 10, or $2,000. You may recall that 95% of the cases in a normal distribution are within 1.96 standard deviations of the mean. To find the lower bound of the 95% confidence interval, we subtract 2,000 times 1.96, or 3,920, from 20,000 to get 16,080. To find the upper bound, we do the same thing, but adding instead to get 23,920. So even though income itself is not normally distributed, the mean is, and so now we can say, if the data were accurate, that there's a 95% probability that our sample confidence interval includes the mean U.S. household income, somewhere between 16,080 and 23,920. It's not precisely the same thing as there being a 95% probability that the true mean is within the confidence interval. But this distinction primarily matters in theory, calculation rather than in application. You can do the same thing with other ranges. A 99% confidence interval, or z plus or minus 2.58, would be $14,840 to $25,160, and so on. There's only one exception, for small samples. Now, there's no precise number here because what counts as small depends in part on how normal the population distribution is, how much precision matters for the estimates. The only difference in calculation, though, is that in small samples, we'll use a cutoff of 30 as a benchmark approximation. You need to use a t-distribution instead of a z-distribution to calculate the width of the interval. T-distributions look normal, but have heavier tails than a normal distribution at low degrees of freedom because, in fact, it's a family of distributions. So each degree of freedom has a different t-distribution that's, for low numbers, more spread out, more platykritotic. For high numbers, looks more like a standard normal distribution. You wouldn't even notice it to look at it most of the time, though. By 30 degrees of freedom, the t and z distributions are almost indistinguishable, which is why you can use the normal distribution or the z-distribution in most cases. Your textbook, the internet, and statistical software will all contain t-tables that can be used just like the z-table we already encountered. alluded before to one more important thing about confidence intervals. They're the first approach we've made to inferential statistics. Descriptive statistics, that is everything to this point, tell us about our data. Inferential statistics use our data to make inferences about a population. With that, we can answer questions such as whether two samples are likely to have come from the same population. But we're not going there quite yet, so just remember for now, use the sample mean and standard error with a z or t cutoff to estimate confidence intervals, which tell us, based on our data, the range within which a statistic of a specific proportion of samples, like 95%, taken from the same population will likely fall. With that, I welcome you to the world of inferential statistics. Thank you for watching.